Two sine waves can have the same frequency, but they can be out of phase. So the other portion of the argument to the sine function is this phase angle theta. So they have the same frequency omega, but they're out of phase by this phase angle theta. So what we want to do is we want to be able to use the terms leading and lagging to represent the general phase relationship between two sine waves. So that angle theta, we can say that's in radians or we can say that's in degrees. So if we look at this example, this shows two sine waves with the same frequency. However, the solid line is the zero has a zero crossing at an angle theta prior to time t is equal to 0. So it has its zero crossing before the dotted line. So we say this solid line is leading by a phase of theta, or what we want to also be able to do is convert that to the time. So we say that our Vm sine omega t plus theta leads Vm sine omega t by theta radians. Or we could say, if we looked at our cosine function here in red, that has at time t is equal to 0, our cosine is equal to 1, so we multiply that by Vm. It's equal to this voltage function then is equal to Vm. The zero crossing occurs 90 degrees prior to that. So we say our Vm sine omega t plus 90 degrees, that's Vm cosine omega t, and our cosine leads our sine by 90 degrees. It leads it because it occurs earlier in time. Right now this is versus omega t, but it occurs earlier in time if we converted that to time. And we'll do that momentarily. So you want to remember that cosine leads sine. C occurs before the alphabet from S, so cosine leads sine. That's one way to help remember it. Sine waves can also be 180 degrees out of phase, and that's like negating. So our sine omega t plus or minus 180 degrees leads Vm sine omega t by 180 degrees, but it also lags it by 180 degrees. They're actually the negating of sine functions is to have a phase shift of 180 degrees. So if Vm sine omega t plus theta leads Vm sine omega t by theta radians, then it's shifted to the left by theta radians, and it occurs earlier in time by theta over omega seconds. So we can calculate that time, we can derive that time. We know the time divided by the period, well, that's going to be the phase angle divided by a complete period, that's 2 pi. So we have seconds divided by seconds, radians divided by radians. From this, then we can get that that time t is equal to theta over 2 pi times the period, and the period is 1 over frequency f. So the time that occurs earlier is equal to theta over omega radians to derive that. And we'll do that in lab. So again, leading or lagging, Vm sine omega t is lagging Vm sine omega t plus theta by theta radians. So leading is shifted to the left, occurs earlier in time. Lagging, shifted to the right, occurs later in time. So if we look at this graph, it says in which graph is the red waveform leading? So it's the red, where is the red waveform occurring earlier in time? And we can see here, it's leading here in this left graph, it's lagging here in the right graph. So that phase angle, let's take a look at that. We can express that in either degrees or in radians. So instead of writing Vm sine, our voltage, we don't have the function of t here. The voltage is 100, that's our Vm, sine 2 pi 1,000. So our omega is 2 pi times 1,000 t minus pi over 6. Our phase shift here then is pi over 6. Well, engineers don't use radians, they use degrees. So we're going to we need to convert pi over 6 to degrees. The simple conversion is radians times 180 degrees over pi is equal to degrees. So what you want to do then is pause this video and evaluate, because you want to be able to use your calculator, at t is equal to 10 to the negative 4 seconds, that's 100 microseconds. what is the voltage of this, what it would be the voltage value at that time for this voltage function. Now, be careful here. So here we have, this is going to be calculated in radians and this is going to be in degrees. So you're going to need to convert one or the other, and you want to know whether your calculator is in degree mode or is in radian mode. Typically in physics, you have it in radian mode. Typically in your engineering classes, you're going to have it in degree mode. So make sure you know that. So again, if we evaluate that, here we show converting to degree mode as engineers. So we convert this 2 pi times 1000 t. We're going to convert that. First we'll plug in for t, that t is equal to 10 to the negative 4 seconds. So we have 0.5, or excuse me, 0.2 times pi. And then we got to convert pi then to degrees. So converting pi to degrees, pi radians is it is 180 degrees, so we can do that conversion of, just to show it, 0.2 pi times 180 degrees divided by pi. That's multiplying it by 1, so that's just equal to 0.2 times 180, or that's equal to our 36 degrees. So then where's 36 degrees minus 30, what we're evaluating is the sine of 6 degrees. You could also convert the 30 degrees to pi, and you should do that and evaluate that also in your calculator. All right, so assuming that you could do that properly, in the next video, we'll look at comparing the phase of two sinusoidal functions.